Well, hi, good morning. Thanks so much for joining me in my shop here. Today, on this video, I'm going to be going over the schematic that you can see here. Now, I tried to set this up so I could do this on camera, but, you know, the schematic is just too fine. There's too much on the page here to put onto a camera. So, that plan didn't work. So, we're going to look at it electronically, which is going to be okay also, except there's two pages involved here, so there's two screens to look at. Unfortunately, it's going to make it a little bit awkward at certain points in looking at the schematic. But my plan is to go through this basically from A to Z and cover the whole thing. I spent too many hours yesterday on my deck looking at this to not try to do 100% job on it. So okay, let's get going on it here. Okay, so as I mentioned, this is only half the schematic. This is the left half. Okay, this part up here is the FM front end, and down here is there isn't really much to show you in terms of an AM front end. And see, I'm already in trouble. I can't even show you the first tube that the AM signal comes into. It's on the other page. So okay, well, we'll just carry on here anyway. So down here in the lower part, this is the switch arrangement. Now this is one of the reasons why I spent hours looking at this thing yesterday, until I noticed, look at the switch arrangement diagram here. So you see above every set of switches there is a button. And pictorially this looks like a set of push buttons. It's actually pretty good. These buttons are the little ones that are in a different location on the cabinet. The ones I couldn't get out of the cabinet. Notice there's only two of them, but there's three buttons on the cabinet. I spent quite a while looking for the third button. I found it. And also look at this. I noticed this right away. The off button appears to be connected to nothing. So didn't look much more closely at it than that until I was forced, while dealing with the FM schematic, to pay attention to this pivot. And then suddenly I realized, oh my gosh, look at this. There's an A here, there's a B here. All through the schematic there are places that say FMA and other places that say FMB. This pivot, this is actually a rocking arm here that connects together mechanically this switch, which is operated from this push button. So when you push this button, it actually pulls this lever, which then operates this set of switches. Until then, until I sort of figured this out, you know, what's obvious is not obvious when you first start looking at these things. I kind of ignored the A and the B, but look, you see there's a FM switch position 18. There's another one over here. So massive confusion I worked my way through. So if you have this radio and you're looking at the schematic, look at this. Don't be fooled. Now what about the third button here, which I spent a long time looking for? Solo speech, the third button is called orchestra. Well, after wasting a fair bit of time looking for it and not finding it, I started thinking a little harder about it. Okay, so wait a minute. When you push orchestra, all you're doing is popping out these two buttons. So these two are off. So there's circuitry that's engaged with the solo button, circuitry that's engaged with the speech button, but no circuitry engaged with the last button. It just mechanically unlocks these two and makes them drop back to the off position. So that took me a long time to sort this stuff out, so I hope you appreciate this. Okay, let's get going here. So we'll start with the antenna, external FM connection, and then here's the AM antenna connection, and you see they are linked here by this little switch arrangement. My impression about how this works, and I may be wrong about this, but I think I got it right. You use a special terminal to plug in your AM antenna. When you do, thrusting it into the little connector at the back of the radio will open this switch. When you pull out the extra external AM antenna connection, the switch closes and connects you to whatever you've got hooked up for an FM antenna. So this is a sneaky way to double duty the FM antenna, which will double as a lousy AM antenna, maybe for shortwave or something like that. So this is very simple stuff, very hard to spot in the radio because it's part of the plug that you plug into. Okay, so carrying on down here, well, the antenna is connected through capacitors right to ground. What's happening here? So you see a tuned coil right here, capacitor which may or may not be part of the deal here. So the purpose of this coil, I guess it would be with this capacitor, 51, 5%. So that's telling you this is a critical capacitor. These two are tuned to the IF frequency of 460 kilohertz. If there's any 460 kilohertz getting to this antenna out of the radio or in whatever way it's getting there, this looks like a short circuit to the chassis. So this basically knocks out the IF frequency should it get to or be coming from the antenna. Maybe another radio with a 460 IF is radiating. Maybe you've got 5 radios. Maybe you've got a shop in your basement with 5 radios going at once. So not all radios have this. This will become more important when we eventually start doing the alignment, because I found an error in the alignment instructions, and this kind of reveals it. So that's what that is. That's the IF trap, I think would be the proper term for that. So what we'll do is we'll carry on through the AM. So you see all these switches here labeled shortwave 1, shortwave 2, broadcast. So these are the sets of coils which are engaged for the different bands, the 3 AM bands that are in this radio. If you look, the kind of things they're doing here, and this is typical, by the way, all these switches are shown in FM position, I think. Okay, I'm not absolutely sure of that. Down here, all the switches are shown off, as if there isn't any button pushed on the front of this radio at all. That's how these are shown. Up here, I think these are all shown in the FM position. And I'll take that back very quickly. No, I don't think they are. So still a little bit of confusion about what position these switches are actually shown in, but let's not worry about that. You can see in the position it's shown here, this coil is just shorted right out to ground. So in some cases, when you push the different buttons here, broadcast, shortwave, shortwave 2, you're not only opening a channel, so to speak, through a set of coils here, you're closing the other ones up. You're shorting them out, making sure that they can't provide any influence. So that's what's going on here, I think. So you have broadcast, shortwave 1, shortwave 2. Signal comes out the other side of this set, or these coils, heads into this switch. Now, let's just take a look here. Here's a ganged capacitor. These are the tuning capacitors for the AM radio. One is tuning the front end here against these coils. The other is tuning against these coils, and these are the local oscillator coils. So this is the set of local oscillator coils. This is the set of front end AM coils. Okay. Now, carry on through here. You can see this is the output from the antenna. It's rising up to this key switch right here. And this, where'd it go? This is the, I think that, I can't remember now. One of these two is the output of the local oscillator for AM. We'll have to look at the other diagram to see that. Or we could switch. We could switch to the camera right now, actually. Take a look at this. Let's just switch to the other schematic. It's just too easy here. And I think the line is right along the edge here, so none of this will reappear. So we need to realize that this top line is the output from this switch. And this switch is selecting the signal from the AM antenna, or it's selecting it from all this stuff, the FM side, which we'll talk about. Look, the signal's already gone through 2 tubes to get to this point on FM. but not on AM. On AM, it's just straight from the antenna all the way to here. Okay, and this is one of those grounding switches. So when you switch this to FM, click, this one moves too, click, and it shorts this line to ground. So there's a fair bit of that going on in this radio, trying to null out the effects of circuits that are not actually needed. Okay, so we'll flip to the other half of the schematic. So this is the line that comes in from the switch. And on this line is either the FM antenna signal, having gone through two tubes we haven't looked at yet, or the AM signal. It's coming right into grid number 1 right here. Now this busy tube with all these grids is the AM mixer tube. It says right there, AM mixer tube. So somehow, okay, so this didn't appear on the other side of the schematic, but here you see a tube and it's labeled oscillator. So you always need some amplification in an oscillator circuit to get it oscillating. Pretty sure that's true. So if we look back over here, we would see that this, well, let's look back over there, why not? Here we go. Okay, so we're looking back over here, and we can see that part of that signal is coming out of all these coils. And I can't sort it out now because the page is split in half and I can't get my head around it. Suffice it to say though, the oscillator signal is coming off this grid. So the grid of the oscillator, a signal is tapped off and fed up to a grid on the mixer tube. So you see in AM mode, you've got the AM antenna signal coming on that grid, local oscillator coming in on this grid, and then you've got a screen in here. It's got 75 volts, actually 120 when you got it switched to AM. See that little half moon? Right there, right there. Little half moon means this measurement is for AM. The other one that's not marked is for FM. So you flip this to FM, screen gets 75 volts. On AM it gets 120. Okay. So coming out of here now, it's still considering the AM signal only, is the mixed signal. So there's all kinds of components here. There'll be the 460 will be here, the antenna signal will be here, and the difference and the sum of those two will be here. So the entire schmozzle of signals coming in on the antenna are here, and they're here again, shifted by the local oscillator frequency. So there's a pile of stuff here. And where's it go? Okay, so it's fed down through here, down through here, down to the B plus supply. That's how the plate gets its B plus from down here. In this schematic, this is what they've done for B plus. It always ends in a little arrow with the amount, the voltage written there. Another thing they've done in this schematic is they put these dark boxes with numbers on them. 2, 3, 4, 5, and onwards, all the way through the schematic. I still at this point don't know what these boxes are. You notice this one, this box number 7, is sitting on a wire to nowhere. So these are test points. The test, I think it's 5, and it says 5 here. So you know, I still haven't quite sorted this out, but this is what a test point is showing like on this schematic. A diamond box with a letter in it. And there's 3 test points shown here, A, C, and B. We will get to them later. But these boxes are different, so I don't know what all these boxes are. Maybe it'll come clear as I keep going. Okay, so coming out of here, as I said, was everything and their uncle coming down through here. Gets to this tuned circuit. This tuned circuit is only happy about things at 460 kilohertz. So only those things and a few nearby things slightly different in frequency from the 460, like maybe 450, 440, going to make it through here. Only weakened 460 should come charging through here quite strongly onto the other side. These coils are in the circuit, but they don't do anything. They aren't reactive at the very low frequency of 460. These are reactive at 10.7 megahertz. Okay, signal gets through here. I looked at this for quite a while. Why are they doing that? Why are they printed on circuit board or unprinted circuit board? Don't know why they showed that. They don't show things that aren't shown for a reason. So there's some reason behind this, and there's some reason why this is curved like this. I couldn't sort it out. Okay, so let's follow the signal though. So the signal generated on the secondary side of this transformer works its way through this coil, shows up on this grid. So we got 460 kilohertz and 450, 470, other things in the neighborhood still here probably, boosted by this tube, thrown through another set of tuned. Wait a minute, did I skip something here? Not exactly. No, I'm okay. I'm okay. So the signal's coming out of here, 460, thrown through these two coils. FM coils don't matter. Comes down here, finds these ones resonate at 460. Now at this point, they managed to throw off everything but 460 and stuff within 10-15 kilohertz of 460. All the rest has been suppressed. So coming on this side, not much left except things oscillating at 460. Whatever antenna signal that was mixed with the mixer frequency, the local oscillator frequency that ended up being 460 is sitting right here. Where does it go from here? Let's see here. Coming out. Bear with me for a moment. This is difficult when all these lines just disappear into space. So 460. Well, let's say the signal's coming out at the top here. See, it goes right to this little diode plate in this tube, which is called the detector. AM detector, not the FM detector, just the AM detector. So there it is. So you're generating, so you're rectifying the 460 here on this line. The audio. So this is the AVC line here. So when you rectify the 460, you get a little DC component, which would normally be just a problem, but in fact radios utilize it to enable automatic volume control. So they arrange the diode here in the circuit to produce a negative voltage relative to the chassis. That's normally how this is done. And that negative voltage anywhere from 0 with no signal to maybe as much as 15, depending upon how all this is done, minus 15 volts. Fed through this resistor, because this is all high impedance circuits here, so we need to close up the dam, so to speak. This is much lower impedance here. And you can also see the audio, whatever's left of the audio is probably forced off this way. There shouldn't, yeah, you don't want the audio coming back this way anyway. What's left here is the DC voltage from the rectified 460, and if you follow this line up, you can see the DC can make it all the way to the grid. So that's what's biasing the grid here. Same thing here. And further on too, on the other part of the schematic. So AVC developed by this tube on this line. The audio's got to make it to this grid. So let's follow back on this sheet. The grid goes back to the volume control. Now if you look at this particular capacitor, it's got this box around it. So this is a shielded capacitor. But, this is a very high impedance circuit here. Look, 10 megohms. So I mean, this is a big antenna. It's going to pick up almost anything. probably, and it's shielded to try to avoid that. So there's a problem with this design, that at this point, this first audio tube can be subjected to noise interference and stuff like that because of the super high impedance of this line. It's just so sensitive. Any tiny charge variation on this piece of wire is going to get amplified. We're going to hear it. So that's why they had to use the shielded capacitor here. Now, if I had stupidly gone and changed this out, which I haven't, not yet anyway, I don't have this kind of capacitor with a ground shield built into it. So hopefully that same capacitor is sitting right there, and hopefully it's okay. So what you're seeing back here is a audio network. These things are common in radios. I think the design engineers had lots of fun figuring this stuff out. There's a number of inputs over here. There's a tape input coming in, phono input. Each one of them has to be treated a little bit differently. And the radio input itself coming in, which has been treated by the earlier stages of the radio. So this is a compensatory network here trying to control the tone quality of the sound. It's not the tone controls, they're over here. There's the treble, there's the bass over here on this side. Once you're past this tube, you get out of this low impedance or high impedance area. But maybe a little easier to hook up more and more circuitry here and not introduce noise and other stuff. So we're going to flip to the other part of the schematic and continue working our way back this way here, just like that. So here we are on the other side. Here's those wires coming across. This one is carrying the AVC voltage. This wire is carrying the FM AVC, which we haven't looked at yet. This one would have the AM AVC voltage. This button showing in FM position. You flip it to AM. The switch goes up here and connects the AM AVC voltage right to the Magic Eye grid. This is what's going to control the way the Magic Eye is operating. If you flip it to FM, the Magic Eye grid gets its signal from, or its voltage if you like, from here, which is coming from the FM detector. Well, that's what's happening down with the Magic Eye. Now, we look over here, we can get thoroughly confused. So here's the phono input, tape input, heading over into that network of capacitors and whatnot, trying to sort out the tonal qualities of these two different sources. And the FM and AM signals are, I've lost track, they're up here somewhere. Let's go back to the other side again. It's all got to get to this grid. It's all got to get to this line here, one way or another. Okay, so now we're down to the audio stage here. So audio amplifier, bass and treble controls. These are both cuts. This is a treble cut, and this is a bass cut. So with these two controls set to their neutral point, which would, in this case would be up here on bass, and treble would be set down here to the bottom of the resistor. That would make the effect of these two capacitors minimal. You get exactly what the radio is putting out. Now, what is the radio? What is the radio circuitry putting out? Is that perfect sound, or is it already discombobulated, too much treble, too much bass? Well, who knows? The guys who designed this radio know, and that's part of what's going on with all these capacitors and stuff. They're trying to correct, perhaps, for audio effects that have occurred earlier in the radio, and they can compensate to some degree. Okay, I don't know that to be a case. I'm making some of this stuff up. But, you know, human beings have a huge power of their imagination to get through stuff, and I'm certainly using mine here. If I run into something that I can't figure out, maybe I'll just imagine it and keep going. It's the keep going factor in human beings. That's what your imagination does for you. Okay, so now we're on the output tube, and the output circuitry, output transformer, things are a little complicated here. So the audio signal's coming in through here. The biasing on this tube is done by lifting the cathode upwards with this resistor. This resistor is going to have a steady voltage drop based on the steady current that flows through this tube without a signal. And that voltage drop will raise the potential of the cathode above the grid, which is where you want it. So you have your two options. You can raise the cathode in voltage by doing this cathode resistor technique, or in this radio you can capture some negative voltage from the rectified IF signals and use that negative voltage, apply it to the grid of these tubes. So see, this one actually says 0 volts on the grid. The grid is actually tied through big resistors right to the chassis. So you can see though, I think this is like 700 and this is 100, so the bulk of the signal is going to find its way this way into here. Maybe that's not quite it's not quite the case here. There's no grid, anyway, I won't go into. The bulk of the signal will end up on the grid under this arrangement. Here we have a screen voltage. This is going to become critical when we look at another part of this radio on the FM side of things, and I'm going to show you something that had me scratching my head and still does. So now the output comes down through the output transformer. This is to power supply. So we go down to the power supply. You see, to low side of primary T2, to tap on primary T2. So these two show here. That forces this coil to be part of the power supply, in fact. So we'll look at the power supply in a moment, but just keep in mind this kind of loops up through here, helping to filter the power supply. Why that doesn't cause a gigantic hum to come out of the speakers, you got me, but it doesn't. So exactly why I can't explain, and I won't. But part of this job of this transformer is actually filtering the DC coming from the radio. Yeah, I find this a little bit confusing here, but nevertheless, the audio signal, which is now quite powerful, quite a range in voltage, being pumped through this output transformer, which then basically it's an impedance matching device to match the voltage current conditions here to what the speaker really wants. The speaker wants lots of current, doesn't care much about the voltage. Tube here wants lots of voltage, doesn't care much about the current. Well, yeah, everybody's got to care about current, okay? But that's the story there. Pretty well. Looks like no feedback. What do we got here? So we do have a connection up through a large resistor. All the way back through here. Okay, so I don't know what this is. Perhaps this is some feedback. Now, most radios, certainly one of this vintage, would utilize feedback, negative feedback, which has a very beneficial effect on distortion. It knocks down the output level a little bit of the radio, but it results in a much less distorted, harmonically distorted, I believe, output. So that's probably what this is. This is probably feedback to help with distortions that have occurred through all these reactive components in that. Now, here's the electrostatic speakers. Now these ones, they don't like current, they like the voltage. So in my radio there's only one speaker, and this probably what they did was they put 3 in later models because one wasn't enough. They put 3 of them to produce enough sound. These aren't very loud, these guys. And where does he get the voltage from to drive it? It's the same voltage that's driving the output transformer. So you have a 255 volts of DC and a swinging audio AC voltage on here, swinging a lot, like I don't know, a couple hundred volts, 100 volts, I don't know how much, a fair bit anyway, swinging within the envelope of this voltage, I could put it that way. And that same swing the DC part's blocked here, and the same swing is sent on down to this speaker. And you got a resistor here, a 1 water. There's a 1 water here. There's a lot of big resistors kicking around here, relatively big resistors. So 18K, yeah, anyway. Now, I think all we're left with at this point is looking at the power supply, which is fairly simple. So here's your plug, goes in the wall, fuse, 6/10 amps. Perhaps this means 6 amps over a long duration will blow this thing. 10 amps will blow it almost instantly. That could be what that means. Not sure. And here's different taps depending upon what kind of voltage you've got at your house. Oh, look, it goes all the way up to 240. So you could even run this radio in Europe or any other location that has 240, 220 type stuff. Of course, here we've got it set for, well, I don't know, one of these, 110 or 125, one of these anyway. And we have two secondaries. One is driving the 2 heaters and obviously the dial light. Oh, there's a fuse in there. Oh, 1.5 inch length of number 32 wire. That's interesting. So I've never noticed this, but I haven't gone looking for it. Now, this tube radio is not relying on tubes to rectify the high voltage. It's using diodes here, which I hadn't noticed, but this is very common in these radios. It's almost always not a silicon diode, but I forgot the name of it now. But a different type of diode here, which these I have heard, I've never experienced this, but if you let one of these fail, they fail in a very smoky, fiery failure, and apparently the smoke that comes out of them is terrible. It can infiltrate your house and stink up your house for a long time or something like that. So a lot of repairs will automatically get rid of this. The other thing about these older style, it still escapes me what they're called. Son of a gun. Where's that coffee? Where's that coffee? These guys over time start developing forward voltage drop of some significance. And as these guys wear out, the more voltage drop they have, the hotter they start getting, and that's the failure mode for these guys. They get really hot and in the end burn away. Okay, let's carry on. So out of here is coming full wave rectified 265 volts. Right away it's encountering a filter cap here, a fairly large one, 100 microfarad. That's probably in that metal one. Up, 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 whoop, whoop, down, 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 up through here, through this winding, back out, and on its way to these different voltage sources. They're all supplied from one spot, yet they all have different, like 235. How do you get this? 210, 235. What's this? 210, 235. So there's that little half moon symbol. So this is the voltage at this point when you flip the radio to AM. It's 235. When you flip it to FM, it's 210. Why is that? I think the reason is, in FM, the radio is drawing more current out of this power supply, and it's just dropping the voltage, probably falling right on this big resistor here. And why on FM are you drawing more power from the power supply? Well, I think you have more tubes engaged. I think it's as simple as that. Let's go back to the other schematic, and we'll follow the FM through here. So here's the 2 FM tubes, which are probably not engaged, probably no B plus to them when the radio's in AM mode, which would be AM broadcast band and the 2 shortwave bands. So with these guys out of the circuit, the heaters are still on, but there's no current flowing through these guys, assumably. Something like that is happening to cause the slightly higher B plus voltage in the radio. And So we'll start over here. Here's your FM antenna connection here. And look, all kinds of coils and capacitors and stuff going on, trying to fiddle around with the signal, get it just right so we can go on the grid of this tube and get a boost. Look, there's still more. Look at it. There's a tunable coil here. These are all tunable things, or adjustable, perhaps I should say. Now, come along to here. This whole thing is the tuner can. See the dotted line there? Where wires go in and out of this can, because of the frequency involved, they actually wrote the capacitive effect passing through the can right there. 1,000 picofarads here too. 1,000 picofarads. Small capacitances make a big deal. That's one of the reasons why this is in a can, and you don't want to fool around with any of this kind of stuff lightly at all. That's what I would say. Now the question is, what is this? So this either means these two components are outside of this can, or they have their own special can in the can. So what are they? So it's a 200 ohm resistor right on the cathode. Now these cathode resistors, this one, here's another one. Oh, that's not a cathode resistor, but just like a cathode resistor, it carries a pretty good chunk of current through the that's passing through the tube. It's a low resistance. My guess is it's a fairly high wattage resistor. These guys may be susceptible to failure. Perhaps they're exposed somehow on this box. I don't know how. Maybe you take the lid off and they're right there under the lid to get at. I don't know. I don't know why they're showing this way, but I suspect it's done because there's a good chance this has failed. Not in my radio. I think my radio is fine. Okay, moving on. We're going to do a whole pile more now of networks of capacitors and coils and all kinds of complex looking stuff. Here's the two tuned capacitors that you are tuning when you turn the tuning dial on the radio. This one is tuning the front end part, probably against this coil here, I think. And this one is tuning against this coil, this part being the local oscillator. So this should be oscillating at 10.7 megahertz here. Probably the signal. Now, exactly how this signal gets mixed up, I'm not so sure. This says FM converter. This is 1/2 of the ECC 85 tube. It's just a triode. How the mixing occurs, I don't know, but it certainly does. So you have the incoming signal around 100 megahertz. You got the 10.7. They mix. And out of here, again, just like on the AM, you get a whole schmozzle of stuff here, including the local oscillator and including the original antenna signals, but now including two more, a difference and a sum of those things. There's an awful lot of stuff on this wire here. There's the FM switch. It's in the AM position, but we can imagine it being clicked to the FM position. And now the output at this point is being fed onto the grid. Okay, so comes through here, gets amplified. This is its tuned transformer for 10.7. Goes on through it, shows up on the grid here, gets amplified, carries on, gets through here. It's ignoring this stuff because this is way off on frequency. This is down at 500, half a million, and this is at 10 million. That's a long ways apart. So the signal doesn't do much down here. If anything, this is where it's concentrated. And now things get pretty interesting. So first of all, there's another coil here. Now they haven't shown it very helpfully here. They would show it better if they moved this coil, the draftsman, and drew it right under this one. What you're really trying to show is that this coil is coupled closely to this coil. This coil has a big fat capacitor hooked up to it here on the other side of the diodes. Okay, so now my imagination is going to talk here for a while. This causes a 90-degree phase shift in what's happening in this circuit right here. 90 degrees from what's happening in this circuit. Because of the close coupling, it's also 90 degrees from what's happening in here. But wait a minute. What's happening in here is wired right into what's happening in here. So this is 90 degrees out from this. Okay, a little bit of magic here. Somehow that generates a, I don't know what to call it, an error voltage. It's not quite right, but a sum and a difference. It's not quite right. A voltage developed because of the phase angle interference between what's happening in this coil because of this big capacitor and what's happening out here. And that phase angle interference results in a AM signal appearing down in here. The AM audio. So you can run a speaker with AM. Of course, speaker needs AM. So from here on in, it's nothing but audio. This goes all the way back and eventually finds its way back to the volume control and carries back on through here. Now AVC voltage is developed, it's going to be developed, well, it's going to be developed through these diodes here. It's going to be present on this wire. It's going to be present here. Ooh, down and out. So you got 1, 2, 3, big jump to 4. 1, 2, 3, big jump to 4. I don't know. I don't know what's going on. But I think if we look at this long enough, we would find out that the DC voltage that's being developed up in here is being applied back to some of the FM tubes. Am I absolutely sure of that? No, I'm not. I'm not. But now to make this guy work, well, in FM, you want to box in the FM signal in terms of its amplitude before it gets to the point where you're trying to do this kind of stuff. Because any AM stuff that's in this FM signal, like a lightning bolt crash, would just come through and it's going to find its way into the audio and out. So in order to get rid of that AM, sort of box in the signal, they usually have a tube called a limiter. And what the limiter does is, how can I make this visual? It's like pushing something through a die. Out the other end comes what you want. That's a terrible. That's a terrible. That's a terrible. Okay, let's say it trims off. It trims off the top and bottom of the FM signal that's coming through here. And what comes out of here is a FM frequency modulated signal with no amplitude variation in it. That's the key to making FM radios quiet. Is this doing that? I don't know. I don't know. Maybe it is. Maybe it is doing that. This is also part of the AM radio circuit too. First AM IF amp. Well, it's the only AM IF amp. I shouldn't say first. I should just say the only, I think. Am I right? I don't know. Anyway, I think we're at the end of the road here. And then the sound comes out of the speaker. Ta-da! Oh, so here's a little goodie here. Let's just look at this table for a minute. Not all schematics have something like this, but because this has this, I'm going to make use of it. So this shows each tube, and this shows the resistance at each tube pin, probably measured to the chassis. This is really helpful. You pull this tube out, stick your ohm meter down into the tube socket, and read the resistance of each pin, and compare it to this table. And if you find anything that's way out of whack, like if it's supposed to be 1 meg and it turns out to be 6 meg, wow, okay, there's a problem there. You can go looking for it. This is a really powerful troubleshooting table for finding things, especially things that aren't kiboshing the radio's operation, but are just disturbing it a little bit, and those things are hard to realize just by listening to a radio. So I'm going to make use of this table. Also littered all through here are little voltage hints, like 100 volts, stuff like that. So I can go through and double check all that stuff too. But the main thing I want to do, and I don't think I'm going to show you this, there are 3 little ugly capacitors on the circuit board that I want to get rid of before I do any more. Right? Those capacitors, they just look. Hey, let me show them to you. Okay, 3 ugly capacitors. Let's look at them with this camera here. There they are. This one, and its brother over there. It says 500 volts, 100 picofarads, I think is what that one says. That one, we don't know how big that is. This one, interestingly enough, somebody's written, that's in pencil. I think somebody took the time to write that. But what exactly did they write there? It looks like 0.1. But anyway, I'll find those on the schematic. Those 3 guys, they look a little scary. This one over here at the end, so yeah, I cleaned him up. He looks better. But I think that last one, maybe that should go too. And you can see this orange one's already been done, so I can double check the size on that. On the other side here, you can see the black capacitor is the big phase shifter in the detector, in the FM detector. Right beside it is this other capacitor. And when you look at it, it says -20 plus minus 70 degrees C. Okay, so I'm not exactly sure what that means, but I'm guessing this is a heat-sensitive component designed to compensate for the radio's temperature while it's operating. And then in between the 2 of them there is a piece of roadkill. That's another capacitor that got beat up at some point and knocked over, and he's fallen down. Maybe he's fine, maybe he's not, but pretty dirty in there, isn't it? And there's one resistor that looks a little odd. This one here. Is that burnt? Or is it stained? This one over here has a bit of black on it too, so I think something got dripped onto it here. That shielded wire we're looking at, that's where the FM signal is brought down and comes in. And see, underneath that coil is some filthy looking thing there. I don't know, that's an ugly looking thing. I don't know what that is. Right in the antenna. Okay, so I'm going to do those 3 capacitors. Having studied up mightily on the schematic, I am now ready to do the alignment. Plus I have studied the alignment instructions, which are all here. Let me show you one thing on these instructions. I'm going to put it up on the screen. No, you know what? I'll leave that for when we go to do the alignment. There's something in these instructions. Anybody who has this exact radio and is following this exact set of instructions for alignment better learn what I learned. Okay, I think that's it for today. I guess it's another beautiful, beautiful day outside, so that's where I'm heading from here. Thanks so much for watching. I hope you enjoyed that, and I hope you got something out of it. See you on the next video.